Resonance structures are different Lewis structures used to represent the same molecule or ion. The atoms remain in the same positions and stay connected to the same atoms. Only the electron pairs are rearranged. Let's begin with the carbonate ion. The carbonate ion is written as CO₃ with a 2- charge. Carbon is placed in the center with 3 oxygen atoms around it. Carbon forms 1 carbon-oxygen double bond and 2 carbon-oxygen single bonds. Each oxygen atom connected by a single bond carries a negative formal charge. The carbon-oxygen double bond can be formed with any one of the 3 oxygen atoms. This gives 3 equivalent resonance structures. Now let's see how we draw the next resonance structure. A double bond contains 2 shared pairs of electrons. The first shared pair forms the sigma bond. The second shared pair forms the pi bond. During resonance, the sigma bonds stay in place. The electrons in the pi bond can be rearranged. First, take a lone pair from one of the negatively charged oxygen atoms. Use a curly arrow to move this lone pair toward the carbon-oxygen single bond. This lone pair becomes a new shared pair of electrons between carbon and oxygen. The carbon-oxygen single bond becomes a double bond. At the same time, the original carbon-oxygen double bond must become a single bond. Use another curly arrow to move the electrons from the pi bond onto the oxygen atom. The oxygen atom receives this electron pair as a new lone pair. The original carbon-oxygen double bond is now a single bond. So, a lone pair forms a new double bond, while the pi bond from the original double bond becomes a lone pair. This creates another valid resonance structure. The carbonate ion has 3 equivalent resonance structures because the double bond can be drawn with any of the 3 oxygen atoms. The actual carbonate ion is a resonance hybrid of all 3 structures. This means the pi electrons are delocalized across all 3 carbon-oxygen bonds. Delocalized means that the electrons are spread across several bonds instead of remaining in one fixed location. Because the pi electrons are spread across all 3 bonds, the 3 carbon-oxygen bonds are identical. Each carbon-oxygen bond has an average bond order of 1.33. Each bond is stronger and shorter than a normal carbon-oxygen single bond, but weaker and longer than a normal carbon-oxygen double bond. Now let's look at ozone. Ozone is written as O3. It contains 3 oxygen atoms connected in a chain. The central oxygen atom is bonded to 2 outer oxygen atoms. In one Lewis structure, there is 1 oxygen-at-oxygen double bond and 1 oxygen-at-oxygen single bond. The outer oxygen connected by the single bond carries a negative formal charge. The central oxygen carries a positive formal charge. To draw the second resonance structure, take a lone pair from the negatively charged outer oxygen. Use a curly arrow to move the lone pair toward the oxygen single bond. This lone pair forms a new pi bond. The oxygen single bond becomes a double bond. At the same time, use another curly arrow to move the pi bond electrons from the original double bond onto the other outer oxygen atom. The original oxygen double bond becomes a single bond. The oxygen atom receives the electron pair as a new lone pair. Once again, a lone pair forms a new double bond, and the pi bond from the original double bond becomes a lone pair. Ozone has 2 equivalent resonance structures. The real ozone molecule is a resonance hybrid of these 2 structures. The pi electrons are delocalized across both oxygen bonds. As a result, both oxygen-oxygen bonds have the same length and the same strength. Each oxygen-oxygen bond has an average bond order of 1.5. Finally, let's look at the nitrate ion. The nitrate ion is written as NO3 with a 1- charge. Nitrogen is placed in the center with 3 oxygen atoms around it. Nitrogen forms 1 nitrogen-oxygen double bond and 2 nitrogen-oxygen single bonds. Each oxygen connected by a single bond carries a negative formal charge. The central nitrogen carries a positive formal charge. The nitrogen-oxygen double bond can be formed with any one of the 3 oxygen atoms. This gives 3 equivalent resonance structures. To draw the next resonance structure, take a lone pair from one of the negatively charged oxygen atoms. Use a curly arrow to move this lone pair toward the nitrogen-oxygen single bond. The lone pair forms a new pi bond. The nitrogen-oxygen single bond becomes a double bond. At the same time, use another curly arrow to move the pi bond electrons from the original nitrogen-oxygen double bond onto the oxygen atom. The original nitrogen-oxygen double bond becomes a single bond. The oxygen atom receives the electron pair as a new lone pair. A lone pair has formed a new double bond, and the pi bond from the original double bond has become a lone pair. The nitrate ion has three equivalent resonance structures. The actual nitrate ion is a resonance hybrid of all three structures. The pi electrons and the negative charge are delocalized across the three oxygen atoms. Because of this delocalization, all three nitrogen-oxygen bonds are identical. Each nitrogen-oxygen bond has an average bond order of 1.33. Resonance makes a molecule or ion more stable because the electrons and charges are spread across several atoms and bonds. The Lewis structures show the different possible arrangements of the electrons. The real molecule or ion is represented by the resonance hybrid. In short, the atoms stay put, the electrons move, and the real structure is a stabilized blend of every valid resonance form.